Mysterious patterns suggest exoplanets could actually be shrinking in the space. Over 4,000 exoplanets orbiting other stars in the Milky Way have been identified and confirmed till date. From that population, a curious pattern has emerged. There are extremely few exoplanets between 1.5 and 2 times the size of the Earth orbiting close to their stars, a phenomenon known as small planet radius gap. Where did they all go? Did they even exist to start with? It's a mystery, but new research may have just brought us closest to the answer. According to the observations, simulations, and modeling, it's likely those exoplanets did exist and shrunk over billions of years. The overarching point is that the planets are not static spheres of rocks and gas we sometimes tend to think of them. Astrophysicist Trevor David of Flatiron Institute in New York City says, the small planet radius gap, first identified in 2017, is interesting because it falls between two classifications of Earth exoplanets: Earth-sized worlds and mini-Neptunes that are smaller than Neptune but still have very thick Neptune-like atmosphere. There are several possible scenarios that scientists have proposed to explain this strange anomaly. One is that they may have just formed that way from clouds of materials that are too sparse to build a Neptune-like atmosphere. But the leading theory is that exoplanets initially formed larger before later shrinking due to the atmospheric loss. This idea has been investigated before, but David and his team added a new parameter to their analysis: the ages of exoplanets which form the same time as their stars. They selected a bunch of exoplanets less than 10 times the size of Earth from California Kepler survey. The data allowed them to accurately obtain the population of the correct size range. Then they calculated the ages of the stars using their chemical composition and light fluctuations. From the two properties that are linked how old the star is. From there, the next step was divide the system into two populations, those younger about 2 billion years and those older. Once they had done so, the researchers noticed an interesting pattern. The mass gap is not completely empty. You see, and the distribution of exoplanets in the gap seemed to be divided by age. For the younger systems, the gap was emptiest in the 1.6 Earth radii region. For the older system, it was emptiest around 1.8 Earth radius. The research team interpreted this to mean that some mini-Neptunes shrink quite dramatically over billions of years, losing their atmospheres to eventually leave just a naked core behind. Above a certain critical limit, the mini-Neptunes have enough mass to gravitationally hold into the atmosphere, resulting in the observed gap. As for what's the causing the atmospheric loss, still this is unknown. So the processes occur on different time scales, both of which in the team observations. This means more analysis is required to determine what exactly is shrinking of exoplanets. Probably both effects are important. David said, but we will need more sophisticated models to tell how much each of them contributes and when. So that leave the two main options. The first is photoevaporation, where the close proximity between the star and the planet is enough for the star's radiation to strip the atmosphere. The second is core cooling, where heat escaping from the planetary core enters the atmosphere and helps strip it away from within. These two different processes occur on different time scales. So more analysis is required to determine what exactly why the shrinking of exoplanets happen. Stay connected and don't forget to click on the subscriber button, and also don't forget to click on the bell icon so that you will be knowing the video which I am going to post next. Thank you for watching.